Hi everyone, today we're going to talk more about electric fields and forces. In particular, we're going to start dealing with them more mathematically and how we deal with multiple charges, multiple fields. First, we have a brief interlude. Pablo is hiding behind
Pablo.
He's wondering what the hell I'm doing. Anyways, before we really get started on all of that, first I want to take a little time just to clarify some of the things that I mentioned in the previous video. So one, here's an example on the left of a field line diagram. It's a little bit like a dipole diagram. There's a negative charge on the left and there's a positive charge on the right. However, this time the charges are not equal in magnitude, and you can see that the resulting field is not exactly what the dipole field looked like last time. Because the positive charge has a greater magnitude, it actually kind of overwhelms the negative charge. If you were to, for example, cover up the left side of this diagram, what we're left with looks kind of like the field of just a point charge. Yeah, it's a little bit bendy, but it doesn't look that different from the field of a regular point charge. But if, on the other hand, I instead cover up the right-hand side, this doesn't look very much at all like the normal field created by a single point charge. So the reason why this is happening is simply because the greater positive charge is kind of overwhelming the negative charge, and we get this looking different pattern. On the right, we have what's often called a parallel plate capacitor. We've got one plate. It looks like a line here, but imagine this is really a two-dimensional sheet, like a thin metal sheet. And likewise over here. And when you put equal and opposite charge, it actually doesn't have to be opposite. But when you put different charges on the two different plates, you create a field that looks kind of like this. And parallel plate capacitors have the interesting feature that the electric field between them is actually almost uniform. It doesn't matter whether you're here next to the positive plate, or here next to the negative charge, or here in between. The field has a constant value from one side to the other. It also doesn't really matter whether you're here, near the top, or here, or here, or here. So this is actually a very practical way, in reality, that we create fields that are almost uniform, which means that it doesn't really change when you move around. Now, there are some caveats. When you get near the edge of the parallel plates, like over here and over here, the fields start to bulge out a little bit. And that's because if you consider being over here, for example, there's just as much positive charge above this point as there is below this point. And so overall, it's going to create a field that points in that direction, because the charges below are going to exert a force kind of in that direction, and the charges above it are going to create a field in that direction, and the charges above it will create a field in this direction. And when you add a vector like this and like this, you end up with something like that. And we could do the same thing with the rightmost charge. So just bear in mind, if you ever do see something like this, if you see a problem and it mentions, oh, there's a parallel plate capacitor, or between two charged parallel plates, the reason why they specify that is because what they're implying is that the electric field is constant. And the assumption is typically that we are not going to be near the ends of it. Something else I'd like to clarify from the last video is, how do we actually qualitatively analyze field strengths from this kind of diagram? Here what we have is a field line diagram. This is a field line diagram corresponding to, who knows, some kind of arbitrary electric field. Who knows where the charges are that made the field? It doesn't really matter. What we're looking at is, this is the field that exists. So one thing to point out is that this is labeled lines of force. This is something that field lines are often called, so it's something you might come across, which is why I'm leaving it there. But I want to emphasize that I'm really not a big fan of this name because it implies that these lines are forces or something like that. But that's really not what they are, right? These are field lines. They tell us what direction the field points. They don't tell us anything about a force because, unless there's a charge here, there is no force here. Forces are acting on objects. Fields fill empty space. So, for example, if I hold a marker up above the ground, I could say that gravity, the force of gravity, the gravitational field from the Earth exerts a force on the marker. But if I take the marker away, the field is still there even though there's no more force. So these don't really represent forces, they represent fields. Fields can exert forces on other charges. So I mentioned in the previous video that the closer together the field lines are, the stronger the field is in that region. It's not perfect. It depends a little bit on how you draw the diagram, but it's a really good rule of thumb. So for example, C here, point C, is right in a region where 3 electric field lines come really close together. So the field lines are really densely packed. If you look over at A and B, you might be tempted to think that the field is stronger at B than at A because B is on a field line and A is not. But that's not really how it works because where I choose to draw my field lines is a bit arbitrary. I could choose to draw a line from starting right here or over here. It's not completely arbitrary. For example, I can't say, oh, I'm going to draw a line right here, and I'm going to draw a line right here, and a line right here, and it's going to make it look like the fields are closely packed here and far apart over there. It turns out that there is actually sort of a systematic way of, if I draw a line here, where should I draw my next line, as long as I only want to draw this number of lines. We're not going to really worry about that, but there is kind of a rule. So if you look at a field line diagram, there's a little bit of a process that goes into which lines we choose to draw. But the fact that I chose to have one here and here is a bit arbitrary because I could have instead, for example, had one here and here instead. And I'd have to, shift all my other lines as well, and they might have slightly different shapes, but it would work just fine as well. What matters is simply how densely packed the lines are in that region. And in this region on the left, the field lines are not densely packed at all. The 2 lines on either side of A are quite far apart from each other, and B is on a line, but the lines on either side are also quite far away. I would say that the spacing over here is not dramatically different from the spacing over here, and so these probably are places with similar magnitudes of electric fields, pointing maybe in slightly different directions. Point D, likewise, is near a line, but it doesn't really matter if a point is near a line. It matters how many lines is it near. And these lines are still quite far apart from each other, maybe not as far apart as the lines over here. And so the field at D is probably a little bit stronger than the fields at A and B, but certainly still weaker than the lines over here. One kind of trick you can do is you can say, well, draw a circle like this and count how many field lines sort of end up inside of this circle. Here we have 3. If we draw the same circle, we want to make sure it's the same size. We see if we centered at B, there's only this one line. So this is going to be a weaker field. If I move the circle around to A, no lines go in it, and this is where the flaw of this is. This doesn't really capture all the information. B happens to be close to one line. A is but far away from any second line. A is not on or very close to either line, but it has a second line that's a little bit closer to it. So this method doesn't work flawlessly. And if I go over to D, we see there's still only one line in it, and so if you just count the number of lines, you're not going to get a perfect picture. But it's good enough for a rough approximation. Now let's move on to the actual meat of this lesson, which is how do we deal with combinations of fields quantitatively. So here I have a diagram with 2 charges, Q1, which has a magnitude of just positive Q, and Q2, which has twice the magnitude of charge, but it is a negative value. Now, what I want to do in this first part is I want to figure out what is the electric field, magnitude and direction, over here at point P. There's no charge at point P. I'm just talking about the field itself. Q1 and Q2 are a distance d apart from each other, and point P is a distance x away from the second charge. So I want to find the total charge or the total field at point P. There's a field everywhere, right? There's an electric field here. It has a magnitude and a direction pointing somewhere, caused by the combination of these two charges. And the way that we do this is, again, as I mentioned before, we simply add fields together. So I just start by calculating the electric field of one of these charges. So let's start with the field from charge 2. In this case, it will be a little bit easier. So one thing is we will almost always put the direction of fields in by hand because it gets really complicated. The math is not really well suited to giving us the direction in these sorts of cases because the positive and negative signs are really telling us are things repelling or attracting. But if things are repelling, one is going to go to the left and one is going to go to the right, and it doesn't really have all the information we need. So we're going to calculate magnitudes, and we're going to call this our positive x direction to the right. So first, I'm going to talk about the magnitude of the electric field at point P created by charge 2. This is equal to K times charge 2 divided by the distance from charge 2 to point P squared. Now the distance in this case is x. P is a distance x away from Q2. And we also know what the charge of Q2 is, but I want to know only the magnitude. So this is going to give me an electric field, in this case, I'm going to put the negative sign in by hand. In this case, putting a negative, keeping the negative sign from Q2 would actually give us the right expression, but we'll see examples in a bit where that's not necessarily going to be the case. So I'm taking the magnitude here and I'm putting this in by hand. I know that the field points to the left from charge 2 because it's a negative charge and field lines point towards negative charges. So at point P, field from charge 2 points to the left, which means a negative number. And when I plug in these numbers, I get minus K times 2Q divided by x squared. That is the magnitude and the direction of the field from charge 2. So the next step is, what is the field from charge 1? Well, it's K times the magnitude of Q1 divided by the distance from from Q1 to P. I'm labeling that R1 for now, but we can see what that is. It's going to be D plus X. But first, the sign. So Q1 is positively charged, which means its fields point away from it. And so the fields from Q1 at point P will point to the right, which is our positive direction. And so I want to put a positive sign in. And again, in this particular example, the signs happen to work out. If I just left the signs from the charges, everything would be fine. It will not always work that way. And if we plug everything in, we get positive K times Q divided by X plus D squared. And so the total electric field at point P is simply the sum of the two. And that gives us K times Q over X plus D squared minus 2K times Q over X squared. We can leave it like this. This is correct. It's the right answer. But it's not necessarily, it might not be immediately obvious to you which one of these is bigger, whether the result is positive or negative. Qualitatively, we can actually tell the field should point to the left because Q2 is a bigger charge, so it's going to generate a stronger field in general than Q1. And it's closer to point P than Q1 is. And so Q2 is going to win overall at point P. Point P is closer to the stronger charge, and so the stronger charge is definitely going to win over the weaker charge that's also farther away. We can see it mathematically. We can factor out the KQ, and then we have 1 over x plus d squared minus 1 over x squared. Sorry, this should be minus 2 over x squared. And hopefully it's clear that this quantity is larger than this quantity because we're dividing those term on the left by a bigger denominator, and we have a larger numerator as well on the right-hand term. So this is going to be negative, and that tells us that our electric field at point P is going to point to the left, and it's going to have this magnitude. Now let's talk about a little bit more of a complicated example where there's things happening in 2 dimensions. So I'm going to keep the same 2 charges. They're the same distance away. We still have charge 1 and charge 2, the same values as before. They're still the same distance d away. This time, however, actually, let's call this not P. Let's just label it a new point. P usually stands for point, so it's nice. But let's call this point, I don't know, how about, what's another good letter? G. Let's talk about, why is it green? Let's talk about point G. So I want to know, what is the electric field at point G? Well, the first thing that we have to worry about is we have these 2 charges, Q1 and Q2. Again, we can figure out the directions already. I don't need to do math to figure out the directions because we know that electric fields point towards negative charges and away from positive charges. So we can draw what these fields should look like. I'm going to draw the field from charge 2 in green and the field from charge 1 in yellow. Hopefully we can see those. So the electric field from charge 1 is positive, so it's going to point away, and that means it's going to point directly downwards. So this we can call the electric field due to charge 1. Now, if the 2 charges were equal magnitude, I would draw the field from the second charge as a smaller vector, because the second one's farther away, so if they had the same charges, this one would have a weaker field, a greater distance away. But this one has twice the value of charge, but it's also farther away, and so it's not immediately obvious how it's going to behave. So I'm just going to draw it with a random size, because I just don't know. I have to do the math first. But I know that it needs to point directly towards the second charge. So now what I need to do is I need to figure out how to combine these. Well, if I want to combine them, first I have to calculate them. But the way that we add vectors, if you remember, is we add vectors by components. So I'm going to have to calculate the magnitudes of E1 and E2, and then I have to find what is the Y component and what is the X component of each one. So let's start. I think it's easiest to start with E1 because it's pointing straight downwards. So first of all, let's create our coordinate system. Let's decide what we want to be positive and negative. So usually we call up positive and to the right positive. And so these are our positive X and Y axes. So let's just stick with that convention. So in that case, we have the following. I know that the magnitude E1 is equal to K times Q1 divided by R1 squared. R1 squared is just Y squared. And if we plug this in, or before we go any farther, I need to worry about the sign. Well, E1 points downwards. We figured that out already, so I need to insert a negative sign. Here you can see an example where the if I just left the sign of the charge in there, it would actually not necessarily give us the right answer. Q1 is positive. It's positive capital Q. And that would never give us this negative sign. I had to put the negative sign in by hand. So generally speaking, that's what you should do in these kinds of problems. Don't try to mathematically determine the direction of a particular field. Do that based off of whether the charge creating it is positive or negative. And so here, this gives us minus k times capital Q over y squared. Now I want to find the x and the y components. And in this case, it's easy. The x component is 0, and the y component is simply the overall field, because it's only pointing in the y direction. Now we need to figure out E2. Well, we can find the magnitude of E2 the same way. E2 is equal in magnitude. So in some ways, honestly, maybe I shouldn't have put the sign in here. I should really have actually said this is positive. The magnitude of the field is positive, but EY is then equal to the negative of the overall magnitude. Because over here we can see, I can't just say E2 is positive or negative because it has two different directions. It has a y and an x component. So I don't know what it means to just put a negative sign in front of the whole thing. But I know that the overall length of this vector is equal in magnitude to k times the magnitude of Q2 divided by R2 squared, where again R2 is the distance from Q2 to point G. And so we can plug this in. This gives us 2 times k times q. And R2 is the length of the hypotenuse of a triangle with lengths d and y. And so R2 is equal to the square root of d squared plus y squared. And then we're going to square it in the denominator here. And so we simply get divided by d squared plus y squared. So this is the magnitude of the second field. To find the x component, well, we simply take the overall thing and we multiply it by the cosine of an angle. Now we have to specify our angle. I already wrote the cosine. So what I want to do is I want my x component to be a cosine just because it makes me happy. So this is going to be our angle theta. It doesn't really matter. I could have worked with the angle down here instead. And then this would be sine of theta. But it'll give us the same result in the end. Now, cosine of theta, we'd have to actually figure out what this angle is. Well, we can do that because the tangent of theta is equal to the opposite side length over the adjacent side length. And so this tells us that theta is equal to the inverse tangent of y over d. Oops. I'm just going to leave that as this. I'm not going to plug this whole thing into here. We can calculate this. If I give you values of y and d, we can find an angle and we can do that. But I am going to elaborate this. I'm going to just simply write this as 2kq over d squared plus y squared times the cosine of theta. Now you'll note I did not put a negative sign here because the x component of E2 is in fact pointing to the right, which is our positive direction. So the next step is we have to figure out what is E2y. Well, that's simply E2 times the sine of theta. And that gives us 2kq over d squared plus y squared times the sine of the same angle. Again, you can see that I don't just want to keep the sign of our charge inside our equation here, because Q2 is a negative value. And so if I left that in, I would have had a negative value over here, over here. And it's not, it's pointing to the right. It's in the positive direction. Likewise, the y component of this is upwards. It's towards this. And upwards is our positive direction. So I don't want to leave the sign of the charge in this equation. I want to get rid of it. The sign of the charge tells me, how do I manually put the direction in? Is it up? Is it to the right? Or is it to the left? Or is it downwards? So we use the sign of the charge to manually put in directions. We don't find the directions using the math. The next step is to put all this together. I'm going to scrunch this all up a little bit just so I don't run out of, or so I have more space. So I want to find the total electric field. That's the combination of these. Well, the total electric field is a vector, and the total x component is simply the sum of the x components of E1 and E2. And since E1x is 0, this is equal, the x component is just equal to E2x, which is 2 times k times q over d squared plus y squared times the cosine of theta, which again we found over here. I can also find EY. EY is equal to E1y plus E2y. And this time I actually have to add things together. Now E1y is negative, E2y is positive. So I'm going to put the second field first. So this gives us 2kq over d squared plus y squared times the sine of theta minus kq over y squared. Right, so just to label this, I have this came from here, and this came from here. So now we have the x and y components of our field. I can represent my total electric field then in two ways. One, is as the x and y component that we found. But oftentimes what I want to do is I want to express it as a magnitude and an angle. I want to know what direction does it point. And we can do that. So the way I drew this particular field, if I add these two together, if I sort of take E2 and I trace it along from E1, or I trace E1 along from E2, we find that our total electric field looks something like this. And so I'm going to call the angle in here phi. And I want to know, again, what is that angle? And I want to know, what is this? Well, the magnitude of the electric field is equal to the square root of its components squared. And since we know what its components are, I can compute that. I'm not going to. It's going to give us a big ugly mess. So I'm gonna leave that be. I don't really care about the final answer. Again, it's just the approach. If I gave you numbers, or if d and y were related to each other, then we could work this out, and we could arrive at a nicer result. And phi can be thought of as the inverse tangent of EY over EX, right? Because phi is the angle right here, and the tangent of theta is equal to the opposite, the y component, over the adjacent, the x component. So this is our result. We can express it either one of these ways, right? So one way of expressing our final result is like this. And the other way of expressing our final result is like this. Obviously, in most cases, it's easier to stop here because we always find EX and EY all in the process of arriving at the magnitude and the angle. But sometimes this is what we really want. It's going to tell us the information that we want more clearly, so it really just depends. This is how you go about adding fields together. The last thing I want to do is I just want to talk about the very first question on the homework, just to make sure we're all on the same page. So here, the instructions, make sure to read them carefully. It specifies that we have one charge, this one, and a second charge, this one. The capital Q has a greater value than the lowercase q, so this is a bigger positive charge. This is a smaller positive charge. And the important part of this that I think is easy to miss is that what we're doing is we're placing a third charge at one of the labeled points on our diagram. So these 2 points are fixed in place, and I am placing a new charge, a third one. And the question is, where could I put this charge so that it experiences 0 net force? Right? That's what this part of this diagram is saying. The net force on this third charge due to the other 2 charges that are already drawn has to be 0. So in other words, I want to know which of these labeled points could I put a third charge. Note that I haven't specified the magnitude of the charge, so that the force would be 0. The reason why it doesn't matter what the third charge is because if the force is 0, if the net force on a charge is equal to 0, well, the net force is equal to the value of the charge times the net electric field. If the net force is 0, then the net field has to be 0 as well. So the question is really asking at which of these points could the electric field be equal to 0? In this particular case, both of these charges will create fields that point away from them. So the field from the charge on the left at point A will point to the left. But the field from the bigger charge will also point to the left at point A. It points away from both of them. So at point A, the field is going to necessarily point to the left. Likewise, at point E, the field is necessarily going to point to the right. That leaves B, C, and D. And in between, if anywhere in between here, the field from the left charge will point to the right, and the field from the right charge will point to the left. The trick here is noting that because the capital Q, the right charge, is bigger than the left charge, it's going to create a stronger field at equal distances. So at point C, the field from the right charge is going to overpower the field from the left charge, and we're going to end up with some force to the left, away from the bigger charge. That'll be an even bigger problem at point D. Now we're closer to the bigger charge, so it's absolutely going to win over the weaker charge. And that leaves point C. So point C is, in fact, the answer. We want to place our third charge at point B. I just realized, actually, so if we go back to our examples over here, what I showed you here is how to add together electric fields. If I wanted to do the same exact thing, but I wanted to place a charge here at point G and say, what is the force on this charge? I can do this in one of 2 ways. One thing I can do is I can first calculate the field at point G like we just did, and then I can say that the force at point G on whatever our charge is equal to the charge that we place at point G times this field that we just calculated. That's one way of doing it. The other option, and I'm not going to go over it because, again, this video is already longer than I want it to be. The other thing that I could do is I could actually say, well, I have charge 1, I have charge 2, and I have charge 3. Let's call this plus Q. Let's call this minus 2Q. And let's call this plus Q again. Well, The other thing is I can just use Coulomb's law, and I know that this is going to experience a force KQ over, let's call this R1 over R1 squared. And it's going to experience an attractive force in this direction with a magnitude of K times Q times 2Q over R2 squared, where this is R2. Once we do that, we can do the same thing. We can then break R2 into its x and its y components. E2 into an x, or F2 into its x and y components. And so this is F1 and this is F2. And we can break the forces into x and y components, and we can do all the same analysis that we did above, skipping over all of the explicit field information. Note that this only works when we're dealing with point charges. Because these are point charges, we can skip straight to Coulomb's law. If we had a more complicated distribution of charges, then Coulomb's law alone is not really enough to do it. We have to figure out the field first. We're not going to be worrying about situations like that in this class. So if I ask you to find the net electric field, you would do something like this. If I ask you to find the net force on a charge, you can use Coulomb's law to start with, skipping the analysis of the fields entirely. Coulomb's law is basically a shortcut that allows us to find the force between 2 point charges. All right, that's it. Hopefully this is helpful, and I'll see you next time.